So we've just seen that assuming that functions that have side effects such as getLine to have normal Haskell types, such as just being a plain string, leads to all sorts of problems. So we get rid of all the development that we've done so far, and we look at the actual solution that Haskell has. And the actual solution that Haskell has is that getLine is not of type string, but it is of type IO string. So we introduce a new type IO. Now this data type IO is abstract. So that means it's different from all the data types we've been discussing so far, right? Whenever we introduced a new data type so far, lists or trees or maybe or either, we always started by giving a definition in terms of these are the constructors and these are the arguments of the constructors. As far as we are concerned, the data type IO does not have any constructors. So there is nothing we could pattern match on. There are no ways that we can directly construct values of the IO type. There are no ways that we can take values of the IO type apart. In fact, we are required to just use functions that exist, separate functions and interface that is being offered to us by the Haskell libraries that allow us to interact with these IO values. There is an implementation, but we can consider that to be internal to GHC. You can actually briefly look at it, because I did encourage you to use the info command a lot. So, I mean, I would not blame you if you tried this yourself. So you can see if you type :IIO, you do actually get its definition. We can see it. It's actually a new type and not a data type. And there is a constructor, and it does have an implementation. It's relatively strange. But you can already see by this constructor here being qualified that it is not exported. So otherwise, it would just write IO if the constructor is called IO, and we could use the constructor ourselves in our own programs, then this would not use the qualified name. The fact that it's using the qualified name here is that it says that the constructor is hidden and we cannot actually use it. So we cannot actually pattern match on something of type IO. We cannot actually construct something using this constructor of type IO ourselves, and this internal implementation is sealed off to us. So for our purposes, we can treat the IO type as being abstract. So what does it mean then? If we don't have like a definition, we have to get an intuition as to what it represents, what it's supposed to express. So the type IO of A is the type of plans to perform effects. Effects being, as I said before, things like networking, disk IO, like interacting with the user, maintaining global state, possibly more things that ultimately yield a value of type A. And now the big idea is that evaluation and execution of these effects are not tied together. So whether or when we evaluate something of type IOA does not matter. It does not trigger the actual side effects. It will at most evaluate the plan. Right? I can easily talk about having all sorts of plans that would involve interacting with the real world if I were to put them in action. So I can say, like, after I finish recording this video, which is already some interaction with the outside world, of course, I will get coffee, then I will drink the coffee, then I will look at my emails, and afterwards I will record the next video. Right? So that is something that describes many steps. Right? It has certain interactions with various different things. It involves the coffee machine, it involves me drinking coffee, it involves recording videos, it involves me interacting with my computer, all these things. But at first, it's only a description, right? And I can talk about the description as if it is a pure value, right? The description itself is completely separate from putting this plan in action and actually doing it. So things represented by the type IOA, at first, they are just descriptions, they are just plans. Right? And so evaluation is just evaluating the plan. When or how you evaluate something, it does not matter for the execution of the actual effects. There is a separate notion now of execution that puts side effects into action. But interestingly, executing a plan is not actually possible from within a Haskell program. And that at first sounds really, really strange. So how can we execute an I/O action then, if execution is separate from evaluation and not really possible from within a Haskell program? What does that mean? Well, we said also again at the beginning of the course that Haskell programs are made up of possibly many modules, and all these modules, they can define various different things by means of declarations. But if we are thinking about a collection of such modules defining an application, then there should actually always be one module in such an application that is being called main with a capital M. The module should be called main. And within that module called main, there should be an identifier being bound that is called main with a lowercase m, like this. And that should be an identifier that has the type IO unit, where the unit type is the type of tuples basically with no components, a type that has just a single interesting value. We're going to discuss this or repeat this again in a few minutes. And this main defined in the main module is supposed to be the entry point into the program. And this is an I/O action. This is a singular I/O action, but possibly a rather complicated I/O action that does many, many things and has many conditions in it and has many steps, right? And this plan, right, that this I/O action evaluates to is the one and only plan that actually gets executed. So, right, when something is evaluated does not matter. It matters whether it ends up being a part of the main plan. And then it will eventually get executed when the program gets executed. We can demonstrate this. So I can actually rename my module here to main. And I can define a main action in here. And I said once at the very beginning, but it's a long time ago, generally you should always name your modules exactly like the file name is mentioned. And main is essentially the only exception from this rule. So you may name any module main, even though it is in a differently called file. So we don't have to rename the file from io.hs to main.hs, although we could. But just setting the module name to main here is fine. And then we can use an IO action here, although getLine is not of the right type. So getLine is of type IO string, and we need something of type IO unit, and we currently really have little, few operations available, right? Little power in our hands. So let's, out of desperation, let's just use a different function that exists that also has IO type. I put string line that takes a string as an argument and then gives us something of exactly the right type that is being expected here, something of type IO unit. And we can do this, for example, by typing, passing the string hello world. So if we apply the string hello world to the put string line function, then the result type is IO unit as we would expect it, and then it fits here, right? And now this is our main plan. And if I now compile the Haskell program by actually invoking GHC and not GHCi on io.hs, see that io.hs gets compiled and there is a binary called io being created. This depends a little bit on the platform you're on. On Windows, this would be called io.exe, right? But on Unix platforms, this will just be called io. And then I can execute the resulting binary. And executing the resulting binary will execute the plan. So I can see that the string hello world will actually be printed out. And it will be printed out without any quotes or whatever. So it's really like the string, the contents of the string will be interpreted. I can also see that if I can put other escape characters in here, like another new line character or a tab character that I can escape in here. If I recompile the program, execute the plan, then these are being interpreted. So there is actual interaction with the terminal going on here, right? And so this is a real side effect that is happening. Yet another example of a function that does have the right type is the write file function. Write file takes a file path and a string and then gives us an IO unit. So file path is something that is worth calling :i on. It's just a type synonym for a string. So all this does is that says that we have two string arguments, but they play a different role. The first one is supposed to be the name of a file that we're writing. The second one is supposed to be the contents of the file that we're supposed to write, or that we're planning to write. So I can call write file test.txt or something like that, and with this hello world content. Okay. And I can check whether test.txt currently exists. No, it does not at the moment. Now if I compile my program again and then run it, I don't see any output now, but the main plan will be put into action. Right, so at this point I should now have test.txt there, and I can actually have a look at it. And it does contain hello world, right? Without a new line at the end now actually, so my prompt here starts exactly afterwards. So perhaps let's put an extra new line in and run this again, and it will overwrite the file. Right? And now we have what we previously got printed directly onto the screen, we now have as the contents of the file. Of course, it is quite tedious if now suddenly, if before, right, we were just using GHCi and we had this nice property that we could just type in expressions and evaluate them and immediately see the results. And now I'm suddenly saying that in order to execute any I/O, we have to make it the main plan and then compile and run the program. And that's the only way to actually execute this. So that is only a partial answer, because there is a second way to execute I/O plans, and that is directly designed for GHCi. And that is to make our lives easier. And that is by just typing in an expression of I/O type into GHCi. If we type in an expression that has IO type into GHCi, then it will deviate from its normal behavior, and the normal behavior being to evaluate the expression and print its result. And instead, it will execute the IO action for us. So evaluate and execute the IO action for us. You can almost pretend like it does write a little Haskell application around your expression, right? Which like makes the expression that you've just written the main program of your application, and then executes that. So that means we can do things much more easily. I could have just called put string line hello world here. And if I hit return now, I also get this plan executed, which is of type IO unit. Right? And I can also call write file test2.txt here with another file with different contents. And let's also put a new line at the end here. And if I type this in, again, this is an expression. I can actually ask for the type of this, which has type IO unit. Right, so if I type this in, it's being executed. And then I can go and look at test2.txt, and it has the contents that I've just been writing. So we can still build small pieces of programs involving IO and work with GHCi as we're used to. It's not all that different from before. Right? GHCi is actually useful to us. It's even better because we can do this even for IO plans that do not have type IO unit. We can do this for IO actions that have a different result type as well, such as getLine. And if I type in getLine into GHCi, it'll also execute the plan, and it will additionally print the final result to us. So that is even more useful in a way. So if I type in getLine and hit return, you see now that there is no immediate answer, and that is because GHCi is starting to execute our plan. And the plan means that it'll wait for me to type something on the keyboard, which is echoed on my terminal. So if I now type hello, for example, you can see what I'm typing, right? But it's still waiting for me to do further input, and it's waiting until I hit the return key, which I'm now going to do. And then the action is complete, and the result of the action is the string hello, and the string hello is printed back to us in addition. The behavior of GHCi is a little bit inconsistent, perhaps, because for IO actions, normally it's executing them and printing the final result to us. But there is this unit thing, which I wanted to mention again anyway, right? So there is this unit type, which you can think of as being a type called unit that has a single value called unit. So it's a relatively uninteresting type. And the IO unit type is being used to describe an IO action where we're not really interested in the result. We're interested in the side effects that it performs to get to the end, right? So it's a common type in the context of IO. Nevertheless, if we print something of type unit, so if I evaluate the unit value, I get it printed back. Right? But if I execute an action of type IO unit, then I don't get anything back. So the final result of an IO action of type IO unit is not printed back to us. That is just intended to be a nicety, right? Because probably it's just noise. There is nothing interesting, no interesting information contained in the unit result. and it would just like cost another line and clutter up our screen. But strictly speaking, it is a little bit inconsistent that if we have something of type IOString, such as getLine, and I type foo and return, I get the string printed back. But if we have something of our type IOUnit, the action is executed as well, but we don't get the unit printed back. That is just something that GHCi does in this way. Right? Nevertheless, we now do have a way to play with I/O actions. There is also, for example, read file, the counterpart to write file, which just gets a file path and then delivers us with an I/O string again, so an I/O action that returns a string. And this behaves as you probably would expect now. We give it a file path, right? Or let's do test2.txt. Let's see whether we still remember what we wrote into that one. If I look at this call, right, read file apply to this file path. Remember, file path is just a synonym for string, right? So we've supplied the file path, so this is an I/O action of type string. If I execute this I/O action by just putting it on to its own line in GHCi and hitting return, then the I/O action is put into action, so it's executed. The file is being read, and we get the string result printed back because it's an I/O string action. So this is a way for us to play with already existing I/O actions. Even though there are libraries now that have functions that return I/O actions for all sorts of different things, this is not getting us very far in terms of writing interesting programs, because yes, we can use I/O actions we already have, but we cannot really compose I/O actions, and that's where the fun really starts, right? We want to do multiple things, not just one thing. We want to wire these things up with certain conditions, or by looping, or by doing interesting things in between. Right? So we don't want to read a single file or write a single line. We want to have interactions with the user or do things as a reaction to something else. And all these things, they require us to have operations that consume I/O actions rather than just produce them, right? That can take I/O actions and do things with them, compose them, put them together, right, in various different ways. And that is what we're going to discuss next.